3 days. But first, before I do that, I want to give you guys a vocabulary term here. Have you guys noticed, whether we do it in class notes or for homework, specifically when you do a reflection, sometimes a point doesn't move. Have you ever noticed that? Like A stays A and it's the same as A prime. It doesn't move anywhere. All right, I want to give that a name now. Those points that don't move anywhere after a transformation called invariant points. Invariant points. All right, again, just get a quick definition. Those are points that do not move after a transformation. Okay, points that don't move. And we've had that come up. Those are invariant. So I just want to test your knowledge here on invariant points before we get to dilations today. But what's about to happen is pain. It will pain me very, very much. I'm asking to do a sketch. I didn't put any graph paper on there. This is everything I go against. Sketching quadrilateral A, B, C, D here. This is disgusting, embarrassing that I'm doing this and having you do it. All right, here's what I'm asking. Name a transformation. So we've gone over 3. Name a transformation where point B is going to be invariant. It's not going to move. Now, let's take all the funny business out of it. Please do not give me translation of 0, 0. A rotation of 360 or 0. A rotation around point B of any degree measure. It won't go anywhere. Let's get more detail, please. All right, let's get above that level. All right, so think of anything I could do here that would, point B would remain just where it is. It would remain invariant. Rotation, reflection, translation. All right, what do you got for me? What could I do here where point B remains the same? Let's go. Now let's go. 7, Amy. Reflection across the line, y equals -3, right? That's what you wanted? Yeah. Amy took the hard one there. All right, I was ready for someone to say the other one. Good job, though, Amy. Good work. We are in honors, so give me another one. Yes, I could reflect over the line y equals 3. I could also do, and I already gave half of it away there. Charlie, where else could I reflect? Look where point B is. If I asked you to reflect over this line, it's not going anywhere. Y-axis. There you go. Yep. Okay, we're all good there? All right, do it for point D now. Give me something, a transformation where point D would not move anywhere now. Point D, if you do what? Point D will remain invariant, not go anywhere. Amy, I'm already heard from you. We're good. I don't want you to steal the hard one anyway. Oh, Josh, here we go.
A reflection of the x-axis.
X-axis, there you go. Reflection over the x-axis. Or, give me another one since we are in honors math. Or, 1-5. Gabby, hello again.
Reflection over x equals 3.
Got it. Vertical line, x equals 3. Good job, everyone. All right, so there's invariant. I didn't know where to put it in the unit. I could have put it in any day we've done so far, but why not the first day dilations? Questions? Invariant, the point or points don't go anywhere. All right, let's move on. Here we go. Now we're on to the final transformation of the 4 dilations. And we're going to spend 3 days on this. Today is an intro. Tomorrow we're going to construct. And day 3, we got to do a line dilation instead of a point. So first, here's your middle school mentality of a dilation. And I got to change that. All right, I got my triangle. I'm going to dilate it. Oh, that means it's going to get larger, or maybe it's going to get smaller, right? All right, that's what happens to a figure. But today's topic is, What happens to a point when you dilate it? Because let's be honest, this ain't happening. Okay, come on. The point doesn't get physically bigger or smaller. All right, so what happens to a point when I dilate it? Here is what happens. You need two things to dilate. Two things. First thing is you need a center to dilate around. Just like rotations, we always need a center to rotate around, right? Well, dilations, we need a center to dilate around. Second thing, probably the most important thing, you need what's called a scale factor. A scale factor. In this case, look at the first diagram I put in your notes. The scale factor is 2. Let me explain to you what that 2 means. Is the point getting bigger physically? No. Here's what's happening. Everyone see point A right now on your paper. Point A. It is a certain distance away from that center I'm dilating around O. It's a certain distance. I don't know how many units, but it's a certain distance. The scale factor 2 tells me I'm about to double that distance away. So see where point A is right now? Look where A prime is. Double the distance away from O. So that's what the scale factor tells me. So points don't get physically bigger or smaller. They either get further away from the center, or take a look at my next diagram. Notice now the scale factor is 1/2. Now they won't get further away. The points actually get closer to the center. Okay, closer. So if your scale factor of 2, they got doubled their distance away. Scale factor of 1/2, they cut their distance in half. Do you see now why figures get smaller and bigger now? Because the points are either getting closer to a center or they're getting further away. All right, that's why they blow up or they shrink. All right, let's fill in this box here. How do I know an enlargement will happen? It will get bigger if your scale factor is bigger than 1. All right, look at our example above. The scale factor was 2. It got larger. Because it's more important for me you understand the because part. Because the points get further away from the center. All right, what would end up being a reduction? Well, I know probably you guys would want to put what? Less than 1? No. A scale factor between 0 and 1. Am I missing anything here for you guys? Usually somebody chimes in at this point and like, what about this then? What about 1? I said bigger than 1 and between 0 and 1. What happens if I dilate by a scale factor of 1? Nothing. Right? Stays the same. Invariant. All the points remain invariant. All right, questions, because we're about to dilate our own points. What's up there?
Why can't you have a negative?
You can. All right, great question. I was waiting, if nobody was going to bring it up, I was going to skip it, but we won't deal with it. But since we're in honors math, let me just show you what happens. Let's say I dilate around the origin, and here's point A. And I have a scale factor of, let's say my scale factor is -2. Here's what happens, all right? The 2 tells me I'm going to get what? Closer or further away? I'm going to get further away from the center, the origin, but on the opposite side. So now instead of A prime being up here, it's actually going to be on the opposite side of the center. So it'll be down here. That's what the negative does. Okay? All right, so it still will double its distance away, but it's just going to be on the opposite side. All right? Good question. Yeah. We can have negatives. All right, let's dilate a little bit. What do you say? Let's do a little dilation. I already plotted point J on there. Can we just make a note of what point, the coordinates of point J, because that's going to come into play here when we do parts A, B, and C at the end. So that's 3, 2. One job. 3, 2. All right, so now we're going to dilate it. First thing I told you was important. What are we dilating around? In this case, the origin. 0, 0 is going to be our center. Our scale factor, 2. First question, is point J going to get closer to 0, 0 or further away? Further away, right? Because if it's bigger than 1, it gets further away. All right, where exactly will it land? We're going to double the distance from the origin to J to find where J prime is. We're going to double the distance. And the way we're going to do that, we're going to do slope. All right, we're going to use slope. So if you take a peek right now, from the center, which is the origin, I'm going to go up 2 over 3 to get the j. Double it. Up 2, or from the center, up 4 over 6. But from j, I can go up 2 again over 3. Notice I've doubled the distance from the origin to j. I've doubled that distance right here. And j prime, let's mark it down. What's that bad boy? 6, 4. All right, part B now, scale factor of 1/2. Now it's going to get closer. How much closer? Half the distance. So remember we went up 2 over 3, cut each in half. Now you're going to go up 1, but over, I know this is awkward, but how many are you going to go over? 1.5. 1.5. There's where j prime is right there. And what's that? 1.5 comma 1. Notice it got closer. And then finally, part C, what about a scale factor of 3 now? So tripling the distance. Well, we already doubled the distance here, right? We went up 2 over 3, up 2 over 3. We doubled it. So let's triple it. Up 2 over another 1, 2, 3. There's where j prime is. So that is how we're dilating. That's what happens to your points. All right, now it's time to talk about a shortcut. You and your group are going to figure out the shortcut. And this shortcut only happens if I dilate around the origin, because we are going to dilate around other points on the graph. But if I dilate around the origin, there's a shortcut how to get to your original point to the prime points. And you and your group are going to discuss that. So here's what I want you to look at to find the shortcut. We always started at 3, 2. I want you to look at 3, 2 to j prime along with your scale factor. There was some type of relationship there, all right, between the scale factor and j prime. All right, so find a shortcut for me. I'll give you guys 2, 3 minutes if you need it to talk in your groups. What's the shortcut so I don't have to use slope? Okay, what's the shortcut so I don't have to use slope anymore?
Are you all in on this English?
Any group confident in their shortcut before we write it down? How can I just go from 3, 2 to 6, 4? Quick. 3, 2 to 1.5, 1. 3, 2 to 9, 6 without going up and over, up and over, up and over. Any group have the shortcut? Confident in your shortcut. This group up front? Multiply by the scale factor. Again, guys, I love this shortcut, and I know you will too, but I have to emphasize you can only use this shortcut if you're dilating around the origin. All right, we're about to do a new problem where we're not, so I can't use this shortcut. So around the origin, multiply the x and y coordinates by the scale factor. Good. Again, only if you're dilating around the origin. All right. Good? Okay. Only if you're dilating around the origin. All righty? All right, well, what happens if we don't dilate around the origin? Nothing. You just can't use the shortcut. We're just going to use slope still. Notice I moved, here we go, in number 2, I moved the center of dilation from the origin to 7, 1 now. So I look, 7, 1, here's the center. So J's either going to get closer to it or further away, depending on the scale factor. All right, scale factor of 2. Let's find out where J prime is. Can I multiply J by 2? No. It's around 7, 1, not the origin. But I still can do slope. Please, when you're doing it, start at the center of dilation. All right, don't start at the point. From the center of dilation, I go up 1 over 4, double it, match it. Up 1 over 1, 2, 3. Here's J prime. Okay? It should always be on the same side. When you start flipping it on the other side, remember we just talked that was negative scale factors, which I'm not going to give you in here. And what's that one? Negative 1, 3. All right, cut it in half now. Instead of going up 1 over 4, up a half over 2. And I'm going to let you guys finish it. So finish parts B and C now. So my goal is you understand what happens now in a dilation. Yes, figures get smaller or bigger, but it's because the points get closer or further away from your center. Part B, dilation of scale factor, well, scale factor of 1/2. Where J prime go here? J prime, Aiden?
5 1/2.
Yep, 5 and 1/2. And how about a dilation of 3? Where'd your coordinates go when you have them? Ooh. Haley?
Negative 5, 4.
Negative 5, 4. Good. Questions? We're all good? All right, so now we dilated points. The last thing we need to do is dilate a figure. All right, dilate a figure. Centered at the origin. Whoa, whoa, hey, good news for you guys. So you can do slope, or you can find the coordinates of A, B, and C and multiply by the scale factor now. All right, you can do the shortcut because the center is the origin. I'll do my version up here. I'll let you guys do yours. All right. You don't need to state them here. You know, obviously you can always write them down, especially if you're multiplying by the scale factor.
Do you have to label the points?
The prime points, yeah. Yeah, we got to know what, like if you put a point there, I don't know if you think that's E prime or A prime. So, all right. Looking good. Everyone's all right. Don't need to say anything, do I? Next up. Okay, let's dilate triangle ABC around point D, scale factor of 2. Can I multiply by 2? Can I multiply everything by 2? No, I cannot. The center is not the origin. So I'm going to have to use slope. Last question before you can do it on your own. Are your points going to get closer or further away from D? Further away from D because the scale factor is bigger than 1. Yep. So make sure when you're doing your slope, you start at point D and go to your coordinate and double it. So if you're going to A, down 1 over 3, match it, down 1 over 1, 2, 3. So here's A prime. All right, so now you know what actually happens in a dilation other than getting bigger and smaller. Heads up, number 30 tonight is going to ask you to find the perimeter of 2 triangles. And since it's going to be graph, the only way you're going to find the perimeter is using distance formula. So I know we've used it a ton. There it is. Okay, so that's number 30 tonight. You're going to be asked to find the perimeter, and you got to use distance formula. Okay? All right. Play your cards right. What's up, Doyle?